Now that Frank has had a chance to speak, I'm in a better position to finish off a few points that I began to make this morning. So what we're looking at is we're looking at these kind of ordered structures. So we had a certain class of, so we had these ordered structures that I was looking at, or orderings, ordered structures. I was looking at here and comparing them to proof theory. So we're looking over here, and I want to just flesh this out a little bit for you so that you can see what's going on. And what we set up was the idea that we have, which means we have a less than or equal to, which is reflexive and transitive. I'll just write RT there. Okay, and here we have an entailment relation, okay, that we're dealing with there. And so what we said is, well, we have something, a greatest element, which we call top, which is A less than or equal to top, which on the proof theoretic side, if you just look at it in terms of true, would be that regardless of whenever A is true, nevertheless top is true in every single case, which is, so it's the trivially true proposition. So we had that. Then we spoke of having meet, so we had this semi-lattice structure. So we have this part is a repeat of this morning, okay? And we wrote this, so we wrote that over here as A and B true entails A true, and A and B true entails B true. So we had that, and then we said it was the greatest lower bound. So we have this, that's as before. That should be B. So then C is less than or equal to A wedge B. So that's the rule. This is so these corresponded to what Frank called the elimination rules. And then the introduction rule is if A true gives us, let's see, B true, let's do this so it lines up. Okay. C true gives us A true, and C true gives us B true. Then C true gives us A and B true. So that's what we said this morning. Then if you add in the additional stuff that Frank did with you, then we also have so we can think of these as just axioms. I'll write a line over them. They're rules with no premises. So then we have the dualization of that. So we have a least element. We have that everything is less than A, but the bottom is less than A. And that's just the idea that if false is true, then anything is true for any A. So that's the elimination form. And then we have the idea that the idea of join. So this is the nullary join. So we have that A is less than or equal to A or B. And we have that B is less than or equal to A or B, or A join B. Because if you think of this as the least upper bound, it's above all an upper bound. So being an upper bound, it means that A true entails A or B true, and B true entails A or B true. So you've got that so far. And then it's the least of all the upper bounds, right? So that says if A is less than or equal to C, and B is less than or equal to C, so if C is an upper bound for A and B, then C has to be at least as big as the join. A or B is less than or equal to C. And as you saw in Frank's lecture, I'll just write it over here. That corresponds to the idea if A true entails C true, and if B true entails C true, then A or B true entails C true. So that's the same, this is the exact same structure, okay, that we have there. And now I didn't quite leave myself enough room. Okay, so that takes care of, so at this point, we have the structure of a lattice. Okay, that's the terminology. So it's a preorder with all finite meets and joins. Okay, so that's just by definition. That's called a lattice. A lot of times, especially in computer science, people throw around the word lattice and think that it can mean anything that they feel like it meaning. Like they'll refer to the subtyping lattice in, Java or something, and it's not a lattice. You don't have joins. Okay, so it's better if we stick to established and meaningful terminology. So this is what is meant by a lattice. So this is a lattice structure. And then in addition, Frank had some rules for implication. And the way I want to do that, there's different ways we can do it. Let me just find what I wrote down here. Give me a second while I find my way. Right. I'll get to that in a minute. Okay. Dun, dun. Where did it go? Oh, there it is. Right. Okay, so one version of it, there are different versions of it. I wanted to write it down clearly. So, which corresponds to the following idea. So one is that one way to write this down is to say, if we know A is true, and we also know that A implies B is true, then we know that B is true. That's an axiom. And another axiom is, another rule that comes up here that says, if C true together with A true gives us that B is true, then with the ambient C true, we know that A implies B is true. So this was the implication introduction, and in one form or another, this is the implication elimination. There's there are slight different ways to formulate it. So for example, you could take this as a premise of the rule and then use the entailment. I mean, there are different formulations of it, but it all sort of amounts to the same thing, okay? And from an order theoretic point of view, what that's saying is you can phrase this in one of two ways. One is to say, A meet B is less than or equal to C if and only if A is less than or equal to either B implies C, or another way that this gets written is C to the B. Written C to the B. Okay? That's the structure. And that's uniquely characterizes this implication connective. That determines it up to isomorphism, and in this case, up to its order identity, being the induced equivalence relation of the preorder. Another way to sort of see this, so that's one way to say it. But if you take, for example, what we can get out of this is if we take, what do I want to say? Give me a moment. Well, anyway, yeah, I think that's the main thing I want to say. And I could also write this down in the following form. That says, if I take A meet A implies B, excuse me, or B to the A, then that's less than or equal to B. That's one way to order it. And if C meet A is less than or equal to B, then C is less than or equal to A implies B, or B to the A. Okay, that's an equivalently. We could either take this definition, okay, one, and when Steve talks, he will explain all the ins and the outs of this too, and we do that. Okay, so in other words, the implication corresponds to an additional closure condition. So we have meets and joins, and we also have what's called an exponential. Okay, so this is the exponential object, C to the B. And such a structure here, which we have going on here, I'll just draw a line. This structure is, my board discipline isn't the greatest. This forms the structure of what's called a High-Ting algebra. That's the definition. And what we're going to do is so the point being that the proof theoretic concepts which are written here, which is this is intuitionistic propositional logic that is written out with and or true, false, and implication. Intuitionistic propositional logic corresponds algebraically to the concept of a High-Ting algebra. So that's the sort of first thing. So this is the sort of algebraic structure. And the High-Ting algebra is an instance of this is called a Cartesian closed preorder. Okay, and Steve will tell you a lot about that. This is a particular case of a category as a preorder, as I mentioned to you before. And being Cartesian means it has a product, which is a Cartesian product that satisfies these conditions here that I mentioned before and drew diagrammatically. And being closed means that it has a exponential that satisfies this condition. And it's an exponential, so it's closed with respect to the Cartesian structure. And so that whole thing is called a Cartesian closed preorder. Okay? So that's the idea. Okay, so generally, in this context, closed means that the maps, the less than or equal to relation, which is the maps between A and B, A less than or equal to B, it can be thought of as the maps from A to B, are internalized as elements of a particular type or an object in the category, which is the exponential object. And that's called a closed structure. And there are situations, I don't remember whether anyone's lecturing on substructural logic this time, but if they were to, then you would run into things called monoidal closed structures, and you would run into other forms of closed structures. I'm not sure if that'll come up in this instance of the summer school. Okay, so that's the notion of a Heiting algebra. And the notion of a Heiting algebra is extremely closely related to the notion of a Boolean algebra. Okay? The only difference is, let's look here, is whether you have a complement. So remember, so what we notice here, if you look at, let me just kind of catch my notes here for a second. Are you with me so far? Oh yeah, I want to say something about, remind me to say something about structural properties. Okay, so here's the idea of a complement. So we define, so Frank defined, I think he wrote it like this, not A by definition to be A implies false. Okay? Or sometimes a notation that people use is A bar maybe. Okay? In certain situations, people like that notation, so you can write one or the other. And this has the feature, okay, that we know that if we take A and A bar, if you look at it algebraically, it's less than or equal to false, less than or equal to bottom. Since bottom is less than or equal to everything, you can really just say it's equal to bottom. Okay? This is a trivial instance of this rule. If you take this principle here, and you make it be A implies false, then you're less than or equal to false. False is less than or equal to everything. So the two together will give you an equation, or the induced equivalence, that is, the equivalence, the induced equivalence of the preorder. But let's just write it like this. So the idea is that this has some of the flavor of negation. Okay, this is called negation. Okay, and in fact, that's the way this is defined. And the other thing you'll notice is that is the following kind of intro principle. This is kind of the elim rule that says if C together with A is less than or equal to bottom, if that's contradictory, then C is less than or equal to A bar or not A, depending on how you look at it. Okay? So this is sort of the introduction rule for negation, and this is kind of the elimination rule for negation. Okay? Now, the thing I want you to see, the thing I want to bring out here, okay, let me catch to this. The reason I want to bring this out, okay, is that, okay, so you're with me so far? Okay, so that's a notion of negation. So any Heiting algebra comes equipped with a notion of negation satisfying these principles by virtue of this definition, okay, because you have an exponential. So that's what I'm saying here. However, there's something to say about this that is worth bringing out because it is of the essence of intuitionistic logic, which we do not, so from an algebraic point of view, is the negation so defined, the internal negation in a Heiting algebra is not a complement in general. That is, what this means is we do not have, well, the best way to say it is it is not the case that top is less than or equal to A or not A. That's the way to say it, okay, in terms of the preorder, okay? In terms of logic, it says we do not expect to be able to prove A or, well, if we write it in logical notation, A or not A is true on the basis of no hypotheses. That's what is going on here, on the basis of no hypotheses. That top being here, assuming, if you think about it as an assumption, you're assuming nothing, or in terms of the order theoretic structure, something is absolutely true means the top is less than or equal to it. Okay, that's the definition. Everything's less than or equal to top. So if top is less than or equal to it, it's true. It's absolutely true. It's not the case that for every single A or not A or its complement, or A or not A, comes out to be true. If that were the case, you would have what is called a Boolean algebra. Okay? So a Boolean algebra is a Heyting algebra with a complementary negation. That is, where the negation behaves as a complement. We have this condition. Okay? But that's a very special case. And why is it a very special case? Because, and now this is a nice opportunity for me to make a point about the nature of constructive logic, which from the show of hands this morning, I have a suspicion that some of you either already know or have intuited, but anyway, let me articulate it for you, okay, because I think it's worth doing it, which is the following idea. It seems superficially that since I don't expect A or not A to be true in general in this intuitionistic setting, it seems as though that's a loss, right? It seems as though something is missing that you're expecting to be true. And so you feel like that's bad because it's a loss. I say, on the contrary, and this was the point that Brouwer made in the 1930s, and no one understood him then, and it's taken a long time for people to understand what he was talking about, which is to say that no, this is not a loss at all. What it is a pure gain. Okay, it is a pure gain. Why? Because we can say, look, a proposition, by definition, we'll say a proposition is decidable if and only if either it or its negation is true. So all that's happening with intuitionistic logic is we're not saying, what we're saying is not every proposition is decidable. And if you take this principle, because it's not always the case that A or not A is true, if you think about that for a minute, if you think about what I was telling you right from the beginning, that we're doing logic as if people matter, what this means is, right, if the fact that there are undecidable propositions is the simple observation that there are unsolved problems. There are problems for which we neither have a proof nor a refutation. A refutation is a function, by this definition, that transforms any proof you think you have into a proof of falsehood. So we'll call that a refutation. So what we're saying is that a proposition is decidable if it has either a proof or a refutation. So if you look at, for example, equality over the natural numbers. So if we have x, y, and n, and now I'm starting to get toward dependent types, but I'll just do it loosely here at the moment. Excuse me, this is a proposition. Okay, so this is a proposition. It's a two-place proposition, and it's supposed to be equality. I claim that this proposition is decidable. That is the idea. Given two numbers, it's clear whether one is equal to the other or not. Okay? If, on the other hand, it were over the reals, then you also could have a proposition. So let's write sub n here just to make it explicit that so we don't get confused by the notation. If we have equality here as another proposition, I claim that this should be decidable. This is not decidable. I can give a proof of that, which I'm not going to do here at the board. But the intuition is, right, you can code up the convergence, for example, of a Turing machine computation as the decimal expansion of a number or as a Cauchy sequence of rationals. And according to whether it somewhere along the way moves away from 0 or not, it's according to whether the machine halts or not. Okay? So there's going to be no way to make this decision. That's just a way of saying it, like a heuristic guide to what a proof would be. Okay, so the point is that, or here's another one, is the famous P is equal to NP conjecture, which expresses a perfectly good proposition, and it's not known whether that is true or false. Okay? So it is very important to understand this point because, you see, the assumption that negation is complementary is the brute assumption that everything is decidable. Every proposition is decidable. Everything is either true or false. So this is what leads to people to characterize conventional logic done with, like, on the basis of a Boolean algebra as kind of omniscient, because it's logic as if people don't matter. The metaphor being, God knows which way it is, so every proposition is either true or false. It's just a matter of whether we know it or not. So from our point of view, as finite beings, from our point of view, it is simply not the case that every proposition is decidable. Now, there's an interesting consequence. There's an interesting subtlety here, which I would like to draw out to make sure you understand, which is the idea that failing to affirm the decidability of every proposition is not the same at all as refuting the decidability of every proposition. Okay? Be on your toes. Okay? Did you understand what I said? Okay? The fact that not every proposition is decidable is not the same thing as saying that every proposition is undecidable. That's a different thing. And as a matter of fact, it's a theorem, and I'll give this to you as an exercise. The theorem of intuitionistic logic that it is not the case that, in general, for every A, this is for generic A, okay, not A or not A. In other words, you have to watch how you read this, because I don't want you to think this is just like some arbitrary game. This is a meaningful statement. It says, intuitionistic logic does not refute the law of excluded middle. Okay? That's what's important. It doesn't affirm it, but it positively does not refute it. It is known not to refute it. So what is so interesting about this? So the proof is an exercise. This is a very interesting exercise. You have everything you need to find this proof. That is, everything that Frank has told you is sufficient to solve this exercise. But I suspect you'll find it a little tricky. It's not that straightforward, okay? In fact, when you do find it, you'll be uncertain whether you're cheating or not, okay, until you go through it a few times. Okay, so I'll leave it as an exercise. But why is this important? It's important because, what is the importance of this? The importance is we can always heuristically assume that a proposition is decidable, even if we don't have a proof that it is. Because, you see, intuitionistic logic is not going to refute the decidability. Okay, that's the idea. It doesn't. If it refuted the decidability of arbitrary proposition, then if you threw in the assumption that it was decidable, then automatically you're in a state of sin, and so everything is inconsistent and it's a mess. But here what we can do is we can make assumptions. We can say, well, suppose we consider that equality on the real numbers, let's say inequality on the real numbers is decidable. Then we can describe, for example, Newton's method for finding roots of a function by a kind of binary search procedure that requires knowing, okay, where are we relative to the x-axis, let us say. You can't actually do that. That's bogus, okay? It's not true, okay? But intuitionistic logic doesn't refute it. So I can throw in that assumption and then act as though it were true. So in other words, the apparent limitations, so this is something that poor Brouwer, could never get across to anyone. The apparent limitations of IL, intuitionistic logic, are the very source of its strength. And its strength and its expressive power. Its strength and expressiveness. You see, it's just pure loss if you impose the blanket assumption that everything is decidable, because you now are unable to draw the distinction between scenarios in which things are decidable and which they're not. Everything has been forced on you, okay, so you can't draw the distinction. Whereas with intuitionistic logic, I can selectively introduce decidability assumptions according to my preference in a particular situation. Maybe I wish to discuss Newton's method, and it's a nice algorithm, but for the fact that you can't compare real numbers for inequality. Okay? So it's a sensible thing to entertain. Whereas if you insist on that holding as a matter of pure logic, then you're out of the game. You can't even play this game. There are many implications of this point, and in fact, when we get to the end, some combination of me and Steve and others will talk about recent advances in type theory that I alluded to earlier that are entirely possible exactly for this reason. Okay? The only reason it works, the reason it's such a beautiful way to go is exactly because of this and related concepts, this idea. Okay, so I think that's a really critical idea to get across. So it's a good thing, okay, to be working with a Heiting algebra and not a Boolean algebra. So what this is saying is that it's one of these things that has the flavor of, puts me in an awkward position as a teacher. It has a flavor of, I have to say to you, in all honesty, everything you know is wrong. Okay? You have to start over. So everybody told you all this story about Boolean algebras. Just forget it, okay? It was a mistake, okay? They led you down the wrong, they're good-meaning people, but they led you down the wrong path, okay? So there's a certain amount of undo that has to happen in order to understand the real theory of programming languages and how it all works. And this is one of them, is getting used to this like core idea. Once you get the idea and start playing around with it, as I say, before very long you'll think, oh my God, these other people are crazy, and that's true, they are, and you'll figure that out. Okay, so that's like a little bit. I wanted to wrap up a little bit that algebraic story because I wanted to bring in the notion of Boolean algebra and compare it to the notion of Heiting algebra. And in order to do that, we needed to develop a bit more of logic so we can see how it works. So now, if you look at it, by the way, if you now go to a conventional textbook that you can download from Amazon, I think you'll be able to put things like the completeness proof for propositional logic will look a lot clearer and cleaner to you than maybe they have before. Okay? Yes?
Are you saying that we should forget about that intuitionistic logic is much better?
Well, classical logic is a special case of intuitionistic logic.
Yeah. But do we know if, how can we know if intuitionistic logic is primitive enough?
We don't.
Okay.
So this goes on in many other such variations. But what I want to be calling attention to here is this was historically was the first move, and in certain technical senses is a very important spot. But it's not to say it's the only move you could make. Okay, so and now that brings me to a second point. Okay, so I'll say it now in order to wrap this up. Okay, so I will answer your question in this way. So the thing I wanted to get across too is I just wanted to relate like textbook treatments of logic to this proof theoretic treatment by bringing out the order structure. A lot of the textbook treatments are not so good, in my opinion, at explaining this idea very well because they don't connect the less than to the idea of entailment. And they don't have at their disposal typically the machinery of natural deduction, which is what Frank was explaining to you before, which makes the whole thing seem natural and inevitable. That's just a personal opinion about why I feel it's so awkward in the usual treatments. But anyway, now you can see pretty clearly what that correspondence is all about and why that's there. I wanted to say one other thing about the properties of entailment. So if you look at, there's one thing I was a little bit fudging earlier, I did that deliberately, was the idea that the entailment has multiple hypotheses. So if you look at this from an algebraic point of view, what is the less than that is in question here? Well, what it is it's the meat of all of these things. Okay? So what you do is we can just relate this to that. Okay, that's the idea. We can think of that as the meat. The reason I bring it up is I want to talk about what are called the structural properties of entailment. And this is, in fact, an answer to the question that was just asked. Okay? So the structural properties we talked about so far, I won't repeat, are reflexivity and transitivity. But in general, we have an additional one. And one of them is called weakening, W, which is usually written like this. If you don't mind, I'll start using the conventional notation, write that gamma. Okay? So what we do is usually say, well, if A is true on the basis of gamma, then surely A is true on the basis of gamma and some other random lemma that has nothing to do with anything. Okay, that's called the principle of weakening. Okay, so that's the idea. So in terms of a preorder, let's look at what's going on. That's saying if gamma is less than or equal to A, then gamma and B is less than or equal to A. Well, for sure, because Is that what I want to say? Yes. If gamma is less than or equal, the reason is that gamma itself is, no, where did I go here? I had the thing in my head. I wanted to show that this is obviously the case. So the idea is that, oh yes, right. So gamma and B is it's a meet. So it's less than or equal to gamma in particular. And that, by assumption, is less than or equal to A. So what the hell did that, oh. So the reason I got confused is because I wrote the wrong letter. I'm thinking, how am I going to do this? Okay, excuse me. Okay, you try this and stand up here and you'll see. Okay? Okay, yeah, so I screwed that up as usual. Okay, so this is less than gamma, which is less than or equal to A by hypothesis, so you'll get the thing below the line. So it's a property of the meet that makes that come out to be true. There are other rules which are called contraction and exchange. And contraction, you might have seen this before, that says, this is an interesting one, that says, let me write it down and then I can explain it to you. It almost looks a little weird. If I can get B on the basis of 2 copies of the same lemma, then I can get B on the basis of 1 copy of that lemma. Okay, that's what that is saying. That's why it's called contraction. So you can almost say it's in the presence of this rule, there's no distinction between the top and the bottom. But in a certain way, you can say, if I appealed to the proof to a particular lemma A twice, then you can sort of appeal to it once and use the result twice. You know, that's essentially what it's saying. So from an order theoretic point of view, this is simply saying if you have gamma and A, and if that's less than or equal to B, then surely gamma and A is less than or equal to B. Well, why? For the same reason I gave before. So this thing is less than that thing, which is less than or equal to B, which is therefore less than or equal to B by transitivity. So that's an easy one. And then there's also exchange. And exchange says, and we'll write it like this to be like as general as I can think of doing, which is to say that the order of the hypotheses doesn't matter. You can do any permutation can be written as a composition of swaps, right? So I just have to work with the 2 swaps. And so from an order theoretic point of view, you can write it out again. You can say, well, this and A and B and delta. If this is less than or equal to C, then this and this and this and, whoops, and delta is less than or equal to C. And the reason is each one of these left-hand sides is less than the other. And you can prove that as an exercise as well. So an exercise, and an exercise that I gave you about excluded middle a minute ago. So these are called the structural properties of entailment, and they're properties of an ordering. That is, they're going to hold in any Heyting algebra by virtue of the fact that we assume that this is a product, that it's a Cartesian preorder. If it were merely a monoidal structure, which is requiring less of the meet, it's not a meet anymore, then these things become interesting. Okay, they're not free in any way. In fact, then one can start introducing things like, if you don't want the order to matter, then that's called a symmetric monoidal structure. Okay, where I can swap those things around. There's a symmetry involved. So that's a game you can play. And so what happens is, in answer to the question, is various combinations of these principles, this one, and this one, are deniable. You can decide not to allow them. I claim you don't have anything even remotely sensible unless you have a preorder. You've got to be able, if you're going to have any notion of entailment at all, it has to be reflexive and transitive. Otherwise, I don't know what we're talking about, okay? That would be what I would say. That's why the axioms of a category, the only thing they assume are identities and composition. If you don't have that, it's like, well, it seems to be not very interesting, okay? So you have to have reflexivity and transitivity. But weakening, contraction, and exchange, those are up for grabs. You can do various things with those. And so in answer to your question, depending on which of these I deny, I get versions, other restricted versions of logic. But they have the same general flavor, the same general principle, which is these restrictions are affordances, right? If I don't have weakening, then I can selectively reintroduce it. If I don't have contraction automatically, I can selectively reintroduce it. You get greater expressive power. It becomes a sharper instrument. Okay? So that's why people are interested in these so-called, what are called substructural logics are ones in which you take only a subset of these structural properties. You maybe miss out weakening, okay? Or you miss out contraction, et cetera. There are various things, okay? All right, so that's like a general, like some general remarks. So I wanted to round out the relation to preorders, and then Steve will pick this up and go full gas on it with treating in the context of categories. So from our point of view, for these couple of weeks, category theory is another way of talking about type theory, which is another way of talking about logic. Okay, so that's what we're doing. So these things are all of a piece. Okay, so that's the idea. Okay, so now I want to go back to these ideas of equivalence. Oh, sorry. Yeah.
Going back to your use the word decidable very carefully, and I wonder if you can say again how it applies to the P equals NP example. On your reading, would you say that
Well, it's not
decidable or not known to be decidable?
Famously, we know that we have neither proof nor refutation of making it. So that's an example of a proposition that at the moment is not decided. So, in other words, I cannot prove either P equals NP or P is not equal to NP, because I can neither prove it nor can I refute it. I neither know that that non-determinism is useless, nor do I know that there's definitely a case where.
I'm trying to pin down what you mean by decidable. So are you saying that P equals NP is not
The
decidable?
definition is whether the A or not A is true.
So are you saying that, for example, P equals NP is not decidable at the moment?
Yes, at this moment, yes. Because it's not the case that I can prove A or not A is true. Okay, yes?
The dream hypothesis. A proof of the dream hypothesis cannot be disproven, but actually be disproved.